So in this particular video, we will be discussing about this relation V is proportional to I, or perhaps V equals to IR. That is how current works. This is current, this is resistance, and this is potential. How these are interrelated in different materials. Now say suppose you have a wire of say length L. Now when we talk about resistance, we are talking about in each segment, say suppose in each segment the hindrance that is a charge is facing while moving. So for me this is how I understand resistance. That is the hindrance that the charge is facing in moving from one point to another. So for me that is resistance. Now say suppose this is of length L. Now hindrance in each point. So now if I just double the length, say this is L, if I join another wire of length L and now I have a potential of V, then for me the resistance has increased. For me the resistance is increased, that is twice R. Now the resistance has increased. So therefore what I can understand is then we know that the current will decrease. If the resistance is increased, the current will decrease. Now, for example, if I maintain the same flow of current, that is, I'm maintaining the same flow of charges with unit time t. So if that happens, what will happen is, it means that the potential must increase because we are just keeping the flow of current constant. If the flow of current is not coming down, and we are increasing the resistance, that could only mean how are we able to keep the flow of current constant? By increasing the difference, increasing the potential difference, and therefore this will be I and this will be twice R. V nu. So V nu is equal to 2 into V naught. That is, if this is my V naught. See, so that is how we can understand. Therefore, we can say that if the length increases, the resistance also increases. So we sometimes in the book you may come across this term, resistance is directly proportional to L, but L is the length of the conductor, say length of the conductor, and R we know is the resistance. So that we are pretty clear of. So now if you look, say suppose in an initial position, if this is V, this is I, this is R. Now if you are increasing, say suppose if you are increasing the resistance, and if you are keeping the current, if you are keeping the potential constant, that is potential is constant. If you are keeping the potential, let's assume this case also potential constant, then for the increase in R there will be the decrease in resistance. Increase in R, decrease in resistance. That means if potential is kept constant, R is inversely proportional to current. What does this particular statement tells us? This particular statement tells us that with the increase in resistance, there will be decrease in current. So this is what we come to know. Now you should also keep in mind, now if you look closely, we also know that suppose this is a wire of cross-sectional area, that is, see suppose this is your wire. So we are talking about this particular area, the width of the wire. We only talk about the length of the wire, but there is a width which we have to consider for the wire. This is known as width, or the most common term that you will come across is cross-sectional area. Cross-sectional area. So this is your cross-sectional area. So now if you look closely, R is inversely proportional to 1 by A. The more cross-sectional area it has, the higher the amount of charge Q can pass. This is the amount of charge that it can pass. Now, I have often seen that people get confused with this length. Length increases your resistivity. That is, the length increases your resisting quantity. But if you increase the cross-sectional area, say suppose if you have increased the cross-sectional area, say suppose this is your wire. This is your wire. We have taken the length to be small and we have taken the cross-sectional area, say suppose this is the radius r, to be quite huge. So we will see that there is an easy flow of current. If you just compare the volume, say this has a particular volume, and for the same volume, if you take this particular wire, now both the volumes are same. Just keep in mind we are talking about volume. So when you compare the area with the high cross-sectional, will have a huge flow of current rather than a wire which has the same volume but the length is increased. So we know that the cross-sectional area is inversely proportional to your resistance. The more area that you have, the less resistance it becomes. And if I take this, R is actually equal to rho by A, that is the property of the matter. This is a property of matter, and this rho is your density. So, and this can also be known as your proportionality constant. So this proportionality constant is related to density. Somewhat you can say this is related to density, but for now you can understand this as your proportionality constant, and it depends upon the material. Now this particular rho or this particular proportionality constant, now this depends upon your material, what type of material it is, rather than your dimensions. That is, it doesn't matter whether the material has this much length or this much width or this much cross-sectional area. This rho is dependent upon the quality of the material. So this is what we can understand or what we can derive further from Ohm's law.